Control Systems Chapter 3, Lecture 3. In this lecture, we'll learn how to convert from a state space representation to a transfer function. So our objective is to explain the process of converting a system from state space to this corresponding transfer function. So why is this important? Well, state space models are useful for modern control design, and transfer functions are useful for classical control analysis and frequency domain methods. And these frequency domain methods are very useful. So the classical approach has certain advantages over the state space approach. However, again, state space approach, as we've learned in the last lecture, is very useful for modeling and simulating in MATLAB. So let's review this. State space representation is again given by the following form. We looked at it in the last lecture. So here x is state vector, u is the input vector, y is the output vector, and we have matrices A, B, C, and D. So finding the transfer function. So let's assume we have, we want to find, we're given the output equation, we want to convert this to a transfer function. So first let's assume zero initial conditions. Let's take the Laplace transform of this equation. So on this side we'll have S times capital X equals A times capital X plus B times capital U. We take this first term and shift it to the left-hand side and factor out the x. And so we have S times I, which is the identity matrix, minus A times X equals B times U. So here all we need to do is solve for X. So X is equal to this term, and notice the minus 1, so we have to find the inversion, and this is a matrix, so we have to invert a matrix. Luckily, MATLAB is good at doing that, times B times U. So that's our output, X. So now we can take this and we can substitute it into the output equation. So we substitute X in, we write y sub s equals C times this X gets substituted in. We can factor, the U is common to both terms, so we can factor that out. Then we can divide by it, so we'll have G equals y sub s over u sub s is given by the following term. So this turns out is our transfer function. So if we know what A, B, C, and D are, we can simply solve this if we can invert this matrix. So let's see how this works. So here's our example from the last lecture. We found this, we were given a transfer function and we found this state space representation. And we found matrices A, B, C, and D. Let's see if we can convert that back to our transfer function. So the first thing we want to do is compute Si minus A. So Si minus A, remember I is the identity matrix, so we'll have simply S times I is going to be S 0, 0S, so minus that. You'll have Si minus A will be this matrix here, so you need to verify that using a piece of paper, see if you can come up with this matrix. Now we have to find the inverse, and so the inverse of this, I'm simply going to show you what it is. I plugged it in MATLAB. MATLAB generated the following equation. And again, this is the hard part here, is finding this inverse. MATLAB generated this equation here, this matrix equation. So step 3, the final step, is to compute G. So G is C times this inverse matrix we found times B plus D. So here C is given, A, B, and D are all given. So you can plug this in and you can come up with our transfer function. And this matches what we had from the second lecture, lecture 2. So here we're back to where we started from. So again, the hard spot with this is finding this inverse, if you can do this inverse. And luckily MATLAB is able to give you help that way. So for practice problem, I'd like you to do the following. Given A, B, C, and D are the following, I want you to come up with the transfer function. And you can verify the transfer function using MATLAB's state space to transfer function. And double check your results. So you may see something like, well, you will see something like this on a future exam. That's it for chapter 3, and we'll launch into chapter 4. I'll see you then.